Hey everyone, Mr. Kim Sing here, and today we're going to be starting off our new topic of indices and specifically the index notation. Before I get into that and all the problems that I'm sure you're excited to get into, I thought I'd start off this lesson a bit differently. And I'm going to show you how mathematics can be conveyed through a very complex tool. I wonder if you can guess it. A very complex mathematical tool. That's right, it's a piece of paper. Did you guess that? So, if you're at home, I'm just going to get you to pause the video, go find yourself a piece of paper, and when you come back, I need you to do a little table like I'm going to do there. Okay, I'll show you what I mean. So can you draw up a table like this for me? Okay, so hopefully by now you've got a piece of paper on hand and you've got a table that looks like this. So on one column you've got this heading, leave a bit of space at the top, folds, and then you've got in the second column rectangles. Okay, we're going to fill this table in. And what we're going to do is we're going to take this piece of paper, I've picked the yellow one to jazz it up a bit, but it really does not affect that at all. Any piece of paper will do. So take your piece of paper. Now what I need you to do is take this and you can fold it in half. So I've got my page vertically, you can fold it in half for me just like this. When you do one fold, make a note of when you unfold it, how many rectangles there are now. We started there and now we have two rectangles, right? So I've done one fold and now I've got two rectangles. And I'm only counting these sort of smaller ones, right? So I understand this is one whole big rectangle. Yeah, we're only looking at how many I've created with the fold on the page. That's what I'm looking at here. So one fold, two rectangles. Let's go again. Two folds. How many do you think there'll be? That's right. There's going to be four folds. This feels like Dora the Explorer now, doesn't it? Two folds gives me four rectangles. All right. Now we're getting a pattern going. So, here's a tricky one. What would three folds give me? I guess what's the pattern? Everyone have a look. Going up by twos, maybe? Or doubling, you think? Let's have a look. Three folds. Can you guys see that? 1, 2, 3, 4, 5, 6, 7, 8. So it does look like it's doubling. Okay, so let's try and confirm this again. Keep going for me, so you can go faster. Four folds. It's getting a little tricky now to do these. So we've got 4 by 4, so that's 16. All right, and just one last one, because I'm actually not sure how many more times I can fold this piece of paper. If anyone knows, please drop me a comment below. What's the maximum number of times you can actually fold a piece of paper? And lo and behold, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 8 by 4, that's going to be 32. Now I would do another one. I don't know if I can actually do it, actually physically folding them, but hopefully by now you sort of realize that this idea of folds and rectangles, the pattern that's happening is each time you fold it, the number of rectangles you're going to get is just going to double. And even if our piece of paper doesn't allow us, we could continue this pattern here if I wanted to, right? And so I guess the question you might have is, what does this have to do with what we're learning about indices and index notation? Absolutely everything. Because when we look at this, we're seeing folds and rectangles on a piece of paper. But to translate this into our mathematical language, what's actually happening is these folds, these are what we call our index or a power. And these rectangles, that's kind of the results we're getting. Sometimes they'll call it a basic numeral. So that's the answer you're getting essentially when you calculate this. And so in order to look at this in terms of a mathematical perspective, if you consider this as 2 to the power 1, what does 2 to the power 1 mean? Well, it's just 2. It's just one value of 2. Nothing very interesting there. Right? 2 squared though, that's the same as 2 times 2, which gives you 4. What's 2 cubed? Now be careful here because don't associate this with multiplying. It's not 2 times 3, it's very different. Right? This is actually 2 times 2 times 2. Right? So it's 2 cubed, or 2 to the power of 3, which means I'm multiplying by itself 3 times. 2 to the power of 4, same thing, right? 2 times 2 times 2 times 2. That gives me 16, all right? 2 to the power of 5, you can imagine what's going on there. 2 times 2 times 2 times 2. I'm running out of room, aren't I? And I'm not even going to try 2 to the power of 6. I'm not going to fit up the page. But can you see, you're only increasing the folds by 1 each time, but you're doubling the result. The same thing is true for our indices, our index, right? You're increasing the power by 1 each time, but we're actually doubling the result each time. And that's very powerful because it means that these things grow very quickly. That's a little taster of what index notation can do and can represent. Some thoughts I'll leave you with. Think about if there's any relationships between these folds and these rectangles. For example, 2 squared and 2 cubed gives me 4 and 8. 2 to the power of 5 gives me 32. So if you can see a little relationship that's happening with these here. Okay. Another thing, just food for thought again, we'll look at this a bit later on, but can we go backwards? Right? We can increase the number of folds as much as you like, or as much as the paper lets us, right? We can keep it going and going and going, and the number will get bigger and make it bigger. What happens if we go backwards? For example, 2 to the power 0, 0 folds. When I started out, how many rectangles did I actually have? If you think carefully, you only have 1. There's no folds at all. There's one big rectangle here, okay? Because there are 0 folds. Try put 2 to the power 0 in your calculator, see what happens. Again, what happens if I go backwards? Again, can you go backwards again? Negative? What's a negative fold? 2 to the negative 1. What's that going to look like? Can you continue the pattern? What's happening? If you're going, each time you're increasing the power, you multiply by 2. What are you going to do if you go backwards? Yeah, you're going to divide by 2, right? So what's 1 divided by 2? That's half. I'm going to look at a little bit of that in more depth later on, but that's just a bit of a taster into what we're looking at today with index notation.